So far in this course, we've actually gone over and learned about a couple of different power series. And the four that you see here are what are known as the four elementary power series. Um, and you're expected to really memorize these and commit these to memory because these are four series that we will be using over and over again to write the power series for more complicated transcendental functions. And we've actually already derived these, or I don't want to say derive, but we've generated these or come up with these in our conversation in sine and cosine when we talked about Maclaurin and Taylor series. We saw where those came from. And these two functions, e to the x and natural log of x, if you go back to our 7.4 video when we discussed the calculus of different power series, we were able to use geometric power series to come up with these series that we have here. And the whole idea behind this first part of the lesson is to use these series that you see below to write the power series for more complicated or more difficult functions. So really, we're just going to dive right into it and start practicing some of these. So I would recommend having these written down on some flashcards or post them up somewhere so that you can start memorizing these because you're going to need to know them. All right, so let's do a really basic example of how we can use these elementary power series to write the power series for the functions that we see below, starting with sine of x squared. So we see that the sine of x squared is really just the elementary series, sine, where what we're plugging in or inputting into our function is x squared. So normally we would write x minus x cubed over 3 factorial. But in place of the x, we're going to just write x squared minus x squared, and we're going to cube this over 3 factorial, plus x squared to the fifth power over 5 factorial, minus x squared to the seventh power over 7 factorial, and so on. And we would just keep doing this. Let me just make this a little bit smaller so we have a little more space to work with. And we would just keep doing this over and over again. And the general term that we have here, this is our a sub n, also should be written in. So we would say -1 to the n times x squared. Again, we're plugging in x squared to the 2n plus 1 over 2n plus 1 factorial. All right. Now, we can leave this as it is, and if we want to, we can just clean up some of these things like x squared to the third power, we would just write as x to the sixth, and so on. And I'm not going to do it for the rest of them. Hopefully you get the idea. All right, so let's try the rest of these. Cosine of root x is just going to be the cosine elementary series that we see here, but we're just inputting root x for all of them. So let's write that out. So cosine of root x is going to be, the first term is 1, minus, and we're going to square our variable. In this case, our variable is root x squared over 2 factorial, which would just be root x, which would just be x, plus, now we have root x to the fourth power, root x to the fourth power over 4 factorial. And you see over and over again what's going to be happening. So then now we have root x to the sixth power, which is just x cubed over 6 factorial. We're going to just keep doing that. And then if we want to look at the general term here, we have -1 raised to the n power, root x that we're now raising to the 2n power, all over 2n factorial. And we have that there. Okay? So these are pretty basic. All we're doing is just plugging in our argument for our trig function into the series. Let's try some other ones, and I'm just going to switch colors so we don't get them mixed up with the work above. Let's take a look at x times e to the x. Well, let me pull that away. X times e to the x, all we're doing here is we're just going to multiply our series for e to the x. Okay, so let me write the series for e to the x. Let me write that out first. We've got 1 plus x squared over 2 plus x cubed over 3 factorial, and so on. But now we're just going to multiply all of this by x. So what does that give me as a result? And you don't have to show this transition step. I could jump right into what I'm about to write, but I just wanted to show you where we're getting this. So we have our series for e to the x, so this would give us x plus x squared plus x cubed over 2 plus x to the fourth over 3 factorial, or you can write 6 also. And then our general term, which is x times x to the n. So x times x to the n would be just x to the n plus 1 over n factorial. And there's our there's our power series for x times e to the x. What about something like number 4? Well, number 4 here, we've got 1 over x. And at first glance, you may not see how this is connected with any of these elementary power series, but if you remember, 1 over x is simply the derivative of the natural log of x. So we can say that this is equal to the derivative of the natural log of x. So if 1 over x is the derivative of natural log of x, then we're just going to differentiate this series for the natural log of x, which would just be 1. So the derivative of x minus 1 is 1. The derivative of x minus 1 squared over 2 is just x minus 1. And if we keep going, we would get x minus 1 squared, and you get the idea. We've got then our general term, which is going to be negative 1 to the n minus 1 times x minus 1 to the n minus 1 power. Okay? All right, so now let's go ahead and try this next one here, number 5. So for number 5, we're now asked to find the definite integral of natural log of x plus 1. Well, let me just underline this in red. So the natural log of x plus 1, well, we got to actually go back to our elementary series here. And if you would go back to our 7.4 video on the calculus of different power series, we said that the series natural log of x plus 1 is actually equal to the following series. We said negative 1 to the n minus 1 times x to the n over n is equal to the following. And if you're not sure how we got that, just go back to our 7.4 video, I believe it was, and we actually wrote that out. So it looks something like this. So in other words, I'm just going to take this, all of this here that we just came up with, and I am going to integrate that. So if we're asked to find the natural log of all this, I'm just going to integrate this series that we have here. And each term, or integrating each term, is pretty straightforward. We're just going to apply the power rule for integration. And since we're finding a definite integral, I'm going to take that integral and evaluate it at t, and then subtract this entire series, the integral of this series, evaluated at 0. So in other words, I'm going to integrate each term, but we're going to plug in t. So this would be t squared over 2. Then this would be t to the third over 6. This would be t to the fourth over 12, t to the fifth over 20, and so on and so forth. And if I then evaluate the integral of this series at 0, it's just going to be 0. So I don't have to worry about writing anything else for that. Let's just go right into the general term. So this would be t to the n plus 1 all over n plus 1 times n. And oh, it looks like this series is alternating, so I've got to also write something for that. So let's write all of this times negative 1 to the n minus 1 power. And again, just to indicate that it's continually, the terms are continuing on. It's an infinite series. Okay. All right. The next couple here, I will do numbers 6 and 8 and give you a chance to try the other ones on your own. So now let's do the reverse process. Let's take a look at this series that we're given here, and let's see if we can come up with a function that represents it. And so again, what we're looking for are patterns with what we see here and any of the elementary series above. So pause the video and see if you can see the connection with what's written here and one of the elementary series above, or maybe some combination of them. Well, if you look at number 6, you'll notice that this looks really similar to that of the natural log of x. Specifically, I should say, this numerator, everything in the numerator appears to be pretty much connected with what is the natural log of x series. Actually, pretty much not only that, but also what we see here in the denominators, right? All of these is really just what's in the denominator. So everything that I have highlighted in green, that's really just the natural log of x. Well, the only difference now is just making sure that I incorporate all of these x's in the denominator. In other words, it's this entire series that I have highlighted in green is the natural log of x series, and we're dividing everything by x. And so just taking the natural log of x series and dividing by x gives you this series that we have here. Okay, let's try number 8 now. Now, number 8, we're trying to find the exact value of this series by using what we know about an elementary series. So again, take a look at what we have here, this particular series here, and ask yourself, does this look at all like any of the elementary series above? So again, pause the video and see if you can recognize it. And hopefully it didn't take you very long because it's pretty identical to what we have above. Clearly, this is the natural log of x series. Well, what are we doing here? We're just replacing all of our x's with an e. So really, this is just the natural log of e. And what is the natural log of e? That's just equal to 1. And I know I said I would just do 6 and 8, but I might as well quickly just do 9 because I recognize that this may not be super clear by just looking at the solutions. So again, look at this series here and look at these series above and see if you can match them up. And hopefully you see that this particular series was sine of x, or really close to sine of x. The only thing that's stopping this from being the sine of x is having a 2. The problem is we don't have a 2 in front. The sine of x series has to start with a 2 minus all of this. Well, fortunately for us, and I should say this, we know if I had a 2 in front here, I would then be able to say that all of this is simply the sine series or the sine function evaluated at 2, right? Because all of our x's are replaced with 2. So the problem is I just don't have a 2 in the front. But we're advanced enough in our mathematics to know that that's an easy workaround. I can easily just add a 2 there as long as I subtract 2 as well. Now I'm not changing the value of this series in any way. So this entire series here is the sine of 2. I just add 2 and subtract 2, which means this entire series here would just be sine 2 minus 2. And while I'm at it, why not? I mean, I've done all the other problems on this page. Might as well just quickly do number 7. This number 7 here, again, we're trying to look at this series and match it up with any elementary series that we do know. And it sure looks like it's the e to the x function, but we're evaluating e to the x at the following arguments, at x squared or negative x squared. So in other words, I would write this as 1 plus negative x squared plus negative x squared squared over 2 factorial minus negative x squared to the third power over 3 factorial, so on. All of this is simply the e to the x function evaluated at negative x squared. So hopefully you can see now how we can leverage the elementary series to help us write series for more difficult or complicated transcendental functions, and then also do things like actually evaluate the exact or find the exact value of specific series or functions using what we know about the elementary series.